Good afternoon, ladies and gentlemen. My name is Karolis Sakalauskas. I am master student at Vilnius Gediminas Technical University. The title of our work is Experimental Investigations of Cracking in Reinforced Concrete Beams of Different Depth. I want to acknowledge my colleagues who contributed to this work, Aleksandr Sokolov, Deividas Rumsys, Darius Bacinskas, and Gintaris Kaklauskas. Special thanks to my thesis supervisor and colleague, Professor Gintaris Kaklauskas, who gave me an opportunity to participate in his scientific research and represent our university in this conference. So, our motivation of this work was that we are currently developing new concept of cracking modeling that need validation by reliable tests. And our work's objective was to investigate the effect of section height, reinforcement ratio, and bar diameter on cracking behavior of RC beams. So, 7 RC steel reinforcement beams of rectangular section were tested at Vilnius Gediminas Technical University. There were 3 smaller beams with section height of 200 millimeters and 4 higher beams with section height of 600 millimeters. The length of smaller beams was about 2.5 meters and the length of larger beams was about 4.5 meters. These flexural members were subjected to a short-term loading under a 4-point bending configuration. Pure bending zone for smaller beams was 1 meter and for higher beams 1.5 meter. Reinforcement ratios of these beams were chosen to be from approximately 0.3 to 2%, and 2 types of bar diameters, 10 and 20 millimeters, were used. These specimens were cast using industrially produced C30-37 concrete mix, and main parameters of these flexural members can later be seen in their names. So, for example, letter S means steel reinforcement, first number means section height, middle number means reinforcement ratio, and the last number means bar diameter. To obtain results of crack spacings and crack widths, digital cameras and electronic microscope were used. And here you can see 2 photos of our test equipment. First photo shows how smaller beams with section height of 200 millimeters were tested. And second photo shows how beams with section height of 600 millimeters were tested. To test shrinkage effects, 3 specimens with section height of approximately 100 millimeters and width of 100 millimeters and the length of 400 millimeters were cast, and shrinkage strains were measured during drying period. Now let's talk about cracking patterns of reinforced concrete beams. As we all know, for flexural members, 2 types of cracks exist, one called primary, other secondary. As we can see from these examples, the main difference between those types of cracks is their height. Primary cracks usually tend to reach neutral axis of the beam, and secondary cracks tend to be smaller than a half of a section height. Here you can see cracking patterns of our 2 tested beams, which height was 200 millimeters. It was observed that for these smaller beams, almost all cracks reached the neutral axis, and no cracks which height is less than a half of section height were formed. So in this case, all these cracks which occurred can be categorized as primary. Also, if we compare these 2 beams, it is clearly seen that beam which reinforcement ratio is smaller. Let me remind you that the middle number means reinforcement ratio has larger crack spacings. Here you can see cracking patterns of our tested flexural members, which height is 600 millimeters. It is clearly seen that for those higher beams, 2 types of cracks have occurred, which is primary higher cracks and secondary. And again, same tendency with crack spacings as with those two previous smaller beams can be seen. Beams with a larger reinforcement ratio tend to have larger crack spacings. And one more example of cracking pattern, you can clearly see higher primary cracks and smaller secondary cracks. As I previously mentioned, crack widths were measured using digital camera and electronic microscope. So here you can see two examples of smaller beams. We can observe how individual cracks with changes with respect to bending moment and how results given by electronic microscope and digital camera correlate with each other. And as you can see, these results correlate quite well. And these are results of beam which height is 600 millimeters, and as well as previous beam, results correlate quite well. And here you can see two different section height beams, 200 millimeters and 600 millimeters, and the evolution of crack widths. Primary cracks marked green and secondary cracks marked red. And you can also see the evolution of mean crack widths, which is marked with black color. Here we can see mean and maximum crack width results obtained with digital camera and electronic microscope. Beam's height is 200 millimeters. First graph shows relation between steel stresses and mean crack width, and other graph shows relation between steel stresses and maximum crack width. From these graphs, we can see that obtained results are almost identical, and here you can see mean and maximum crack width results of a beam which height is 600 millimeters. For both examples, we see that results of mean and maximum crack widths obtained from digital camera and electronic microscope are almost identical. So probability that crack widths were measured inaccurately is quite low, and the results can be said to be reliable. After all measurements, obtained test values of crack spacings and crack widths were compared to predicted values by Eurocode 2 and Model Code 2010. Here we can see the statistics of mean crack spacings. It was observed that for flexural members which reinforcement ratio is lower, for example, the beams number 1, 4, and 6 marked with yellow color, Eurocode and model code tend to give larger values than actually are. And these differences between test and theoretical values are quite large. And ratio between mean crack spacings obtained from codes and mean crack spacings obtained from tests are shown in the last columns, two columns. Here you can see the results of maximum crack spacings, and similar to mean crack spacing, theoretical values for beams with lower reinforcement ratio are larger than test values. Same tendencies can be observed when analyzing mean crack widths. It is clearly seen that for beams with larger reinforcement ratio, I want to remind you once again that middle number means reinforcement ratio. For that beams with larger reinforcement ratio, predictions for larger reinforcement ratio, predictions by Eurocode 2 and Model Code 2010 were close to test results. But however, for flexural members with lower reinforcement ratios, Eurocode and Model Code gives larger values compared to test. The same situation as for maximum crack widths. Here you can see the examples of specimens with higher reinforcement ratio. and for these elements, codes give quite accurate results. And here you can see the examples of elements which reinforcement ratio is about 0.35%. And for those elements, we can notice that Eurocode and modal code give values larger than experimental results. And here we can see the comparison of predicted mean values by codes versus values obtained from experiment results at 300 megapascals reinforcement stresses. And again, when we are analyzing the statistics of specimens with lower reinforcement ratio, which is the first, the fourth, and the sixth element, Eurocode and modal code tends to give slightly larger average values. And here you can see similar tendencies with maximum crack widths. And again, for members with lower reinforcement ratio, codes give larger values, up to 2 times if you see, for example, Eurocode and modal code. And in conclusion, I want to say, although reinforced concrete exists many years, there are many questions left to answer, and only we, colleague scientists, can answer those questions. Thank you for your attention.